Hello everyone, today I will deliver a lecture on comparison test for positive term series. Comparison test 1 or first type. If sigma un and sigma vn are two positive term series and k not equal to 0, a fixed positive real number independent of n, and there exists a positive integer m such that un less than or equal to k times vn for all n greater than or equal to m, then sigma un is convergent if sigma vn is convergent, and sigma vn is divergent if sigma un is divergent. Proof: let n is greater than or equal to m, Sn is equal to u1 plus u2 plus up to un, and Tn is equal to v1 plus v2 plus vn. These are the partial sums of the series sigma un and sigma vn respectively. Now for all n is greater than or equal to m, we have Sn minus Sm is equal to um plus 1 plus um plus 2 plus un, which is less than or equal to k times v plus 1 k times v m plus 1 plus vm plus 2 up to vn. यहाँ पे n m से बड़ा है, तो जो भी टर्म शुरू होगा यहाँ u1 प्लस u2 प्लस अप टू ये बीच में होगा u2 और u1 के बीच में, यानी कि un से पहले होगा mth टर्म. सो u1 प्लस u2 प्लस अप टू um प्लस 1 अप टू un. तो जब Sn और Sm के बीच में हम डिफरेंस लेंगे तो ये वाला टर्म रिमेनिंग रहेगा, which is equal to k times Tn minus Tm. This quantity is equal to Tn minus Tm. Therefore, Sn is less than or equal to k times Tn plus Sm minus k times Tm, which implies that Sn less than or equal to k times Tn plus h, where h is equal to Sm minus k times Tm, a finite quantity. Now, first part, if sigma vn is convergent, then the sequence Tn of its partial sums is bounded above, so that there exists a number b such that Tn is less than or equal to b for all n, because Tn is bounded above. So Tn is bounded above by this quantity b. Therefore, from equation 1, this is equation 1, we have Sn is less than or equal to k times b plus h for all n greater than or equal to m. Therefore, the sequence Sn is also bounded above by this quantity kb plus h. Hence, sigma un is convergent. So, this proves the first part of the theorem. That is, if sigma un is convergent, then sigma un is convergent. Second part, if sigma un is divergent, then the sequence Sn of its partial sums is not bounded above, so that if g be any number however large, there exists a positive integer m 0 such that Sn is greater than z for all n greater than or equal to m0. Thus, from equation 1, for all n greater than or equal to maximum of m and m0, Tn is greater than or equal to 1 by k into g minus h, where k is not equal to 0, which is given. Therefore, the sequence Tn is unbounded, because Tn is greater than or equal to this quantity and g is very large number. Therefore, the sequence Tn is unbounded and hence sigma Vn is divergent. Test 2 or limit form. If sigma un and sigma Vn are two positive term series such that limit n tends to infinity un by Vn is equal to L, where L is a non-zero finite number, then the two series converge or diverge together. Here L is greater than 0, because L is non-zero and sigma un and sigma Vn are two positive term series. So, therefore, L must be greater than 0. Let epsilon be a positive number such that L minus epsilon greater than 0. Since limit n tends to infinity un by Vn is equal to L, therefore, there exists a positive integer m such that modulus un by Vn minus L less than epsilon for all n greater than or equal to m implies that L minus epsilon less than un by Vn less than L plus epsilon for all n greater than or equal to m, which implies that L minus epsilon Vn less than un less than L plus epsilon Vn for all n greater than or equal to 1. For all n greater than or equal to m. This is equation number 1. Now, if sigma Vn is convergent, then from 1, un is less than L plus epsilon less than Vn for all n greater than or equal to m. So, by test 1, sigma un is convergent. Again, if sigma Vn is divergent, then from equation 1, un is greater than L minus epsilon Vn for all n greater than or equal to m. Again, by test 1, sigma un is divergent. Similarly, we can show that sigma Vn converges or diverges with sigma un. Hence, two series behave alike. That is, either two series converge together or two series diverge together. Comparison test second type. If sigma un and sigma Vn are two positive term series and there exists a positive integer m such that un by un plus 1 is greater than or equal to Vn by Vn plus 1 for all n greater than or equal to m, then sigma un is convergent if sigma Vn is convergent, and sigma Vn is divergent if sigma un is divergent. Let Sn is equal to u1 plus u2 plus up to un and Tn is equal to v1 plus v2 plus up to vn. For n greater than or equal to m, we have um by un is equal to um by um plus 1 into um plus 1 by um plus 2 dot dot up to un minus 1 by un, which is greater than or equal to Vn by Vm plus 1 into Vm plus 1 by Vm plus 2 up to Vn minus 1 by Vn, which is equal to Vm by Vn, implies that un is less than or equal to um by Vm into Vn for all n greater than or equal to m. Since m is a fixed positive integer, therefore um by Vm is a fixed number, say k. Therefore, for all n greater than or equal to m, we have un is less than or equal to k times Vn. Hence, by test 1, sigma un is convergent if sigma Vn is convergent, and sigma Vn diverges if sigma un diverges. Remarks. For practical purposes, test 2 is very useful and can be easily applied. For a successful application of the comparison test, we first make an estimate of the magnitude of the general term un of the given series, and then select the auxiliary series sigma Vn of such a magnitude that limit n tends to infinity un by Vn is equal to L, which is not equal to 0 or infinity, or in other words, un is equivalent to Vn. Thus, for large values of n, square root of n cube plus 1 is equivalent to n raised to the power 2 by 3, n to the power p by 1 plus n to the power 1 plus n raised to the power q is equivalent to n raised to the power p minus q. Sin 1 by n is equivalent to 1 by n. Number 3, it will help to remember for large n that e raised to the power an is very greater than n raised to the power p, and which is very greater than log n raised to the power c, where a, b, c are positive real numbers. Solved examples. Show that the series 1 plus 1 by factorial 2 plus 1 by factorial 3 plus up to infinity is convergent. Solution. We have 1 by factorial 2 is equal to half. 1 by factorial 3 is equal to 1 by 6, which is less than 1 by 4 is equal to 1 by 2 square. 1 by factorial 4 is equal to 1 by 24, which is less than 1 by 2 cube is equal to 1 by 8. Similarly, 1 by factorial n is less than 1 by 2 raised to the power n minus 1. Therefore 1 plus 1 by factorial 2 plus 1 by factorial 3 plus up to infinity is less than 1 plus half plus 1 by 2 square plus up to infinity. Thus, each term of the given series after the second is less than the corresponding term of the convergent geometric series 1 plus half plus 1 by 2 square plus up to infinity. Thus, by test 1, the given series is convergent. Example 2. Show that the series 1 by log 2 raised to the power p plus 1 by log 3 raised to the power p plus 1 by log 4 raised to the power p up to 1 by log n raised to the power p plus up to infinity diverges for p greater than 0. Solution. Since limit n tends to infinity, log n raised to the power p by n is equal to 0. So, logarithm n raised to the power p is less than n for all n greater than 1. Therefore, 1 by log n raised to the power p is greater than 1 by n for all n greater than 1. Now, compare the given series with the divergent series half plus 1/3 plus 1 by 4 up to infinity. Since each term of the given series is greater than the corresponding term of the divergent series, therefore by test 1 the given series is divergent. Example 3. Investigate the behavior of the series whose nth term is sin 1 by n. Let un is equal to sin 1 by n and vn is equal to 1 by n. Now limit n tends to infinity un by vn is equal to limit n tends to infinity sin 1 by n by 1 by n is equal to 1. Therefore, two series behave alike. Since sigma vn diverges, here sigma vn is equal to sigma 1 by n. Since sigma vn diverges, therefore sigma sin 1 by n is divergent. Example 4. Test for convergence of the series sigma n equal to 1 to infinite 1 by n square log n. We know that 1 by n square log n is less than 1 by n square for all n greater than or equal to 3. Since sigma 1 by n square converges, so by first comparison test sigma n equal to 1 to infinite 1 by n square log n converges. Thank you very much for watching this video. Please subscribe my channel. Please like, share and comment on this video. Please press the bell icon to get notifications.